This video I want to give an overview of the approach that we take in this lab to acquiring dynamic signals by setting up a computer data acquisition system using Python with Arduino. First of all, there are a lot of different types of DAQ or data acquisition systems. I'm showing a couple here. A very common one is those built by National Instruments. You can find more information at ni.com. A lot of those systems now require the use of LabVIEW software, or even if you want to use Python, it's restricted to Windows and Linux. They do have drivers that allow you to use that and access devices that they make. These aren't the only types of devices. There's a lot of different options for data acquisition, hardware, software combinations. I also like the LabJack devices, fairly low cost. And the nice thing about the LabJack is it's available not only for Windows, Linux, but also you can use it on Mac with some other drivers. So you can use Python programs to access these data acquisition systems. Again, the difference between a DAQ system of this sort is that the hardware is designed to acquire signals. Usually it'll have a buffer on board. You send it a command, say, hey, collect, X number of channels of data, store it, and then there might be a command that transfers it over as part of a command that transfers it over. But it's designed to collect, data, and that's what it does. It's its principal purpose. And there's a lot of different kinds of, again, devices that have been made over the years for doing this, with computer support, right? In this lab, we're keeping things low cost and open source and have adopted Arduino for that. Now, the Arduino is a microcontroller, as we've discussed before. It's not, strictly speaking, a DAQ device, even though it does have the ability to collect analog signals, digital signals. It can communicate with smart sensors through bus interfaces and so on, serial communications and so on. So it really is very useful. It also works with software in a loop type structure. So it's always having to do something, right? Once you put a program onto Arduino, it's going to do this continuously. So if you write a program that collects data, it's always taking that data unless you reset it and have it stop and so on. Again, there's exceptions, I'm sure, but primarily, you're right, it's a controller, so it's doing something continuously. It's useful for writing little control programs and controlling robots and all kinds of processes and so on. It does have some limitations. I mean, these are very low-cost devices, but for our purposes of this lab, we can create studies that match the capabilities of Arduino, and there are some limitations. So, again, we want to continue learning about what's on board, and you should be familiar with the Arduino from your previous study of the Arduino. And again, you always continuously kind of update that knowledge based on what the requirements are of any particular application. Now, grabbing analog data from any kind of device, again, if you use a DAQ device, you can look at some of these sites, and they talk about what kind of software they can use and so on. Again, there's some restrictions on some devices. They may be available for certain platforms. Again, an advantage of a DAQ device is it's designed to collect data, simple online functions. It might have also very high rates of data acquisition, right? If you have an application that requires megahertz, gigahertz, usually you use specialized instruments for that, or they might also have very high fidelity. In other words, you get many number of bits for collecting and resolving, voltages, and it might have particular bus protocols. Again, there's so many different applications for how we need to acquire data that dictate how we need to acquire data, control and experiment, so on. That you have to just be mindful of the fact that there's a wide spectrum of technology out there for doing that. The Arduino DAQ is much more limited, again, but it's open, it's low cost. I like that part of it. But there are some steps that we are taking, and you'll start learning about some of them in this coming lab. We don't require you to write the code to do this from scratch. We'll give you the code. You can begin digging into it. Some of the things you don't have to, we'll always give you the code that works for a particular lab, but it's useful to start, and I'll maybe show, if I have some time here, I'll show you where to look for certain things that you can change if you ever use it for a different application. This first lab we're gonna focus on analog input. Subsequent labs will be communicating with sensors that through I2C and so on. We're not taking analog voltages. We're grabbing data that's been collected on that sensor. But this one we're going to be measuring voltage directly from a potentiometer on the pendulum. Part of what you need to do is understand how Arduino and Python both communicate serially, right? We're going to have a USB connection. So there's other ways to communicate with Arduino. You can use wireless, Wi-Fi, Bluetooth. There's a lot of different ways to get data onto a different platform. Let's say from an Arduino platform to your computer. We just like to use the USB. It's convenient for acquiring lots of data, and we don't have a Wi-Fi connection in this application, but you could do that. And also just again understanding how Arduino is running in a loop. So you have to be mindful of how that also dictates how fast it can run, and also how fast you can acquire data. And that's actually one of the really important things to keep in mind. I'll mention at the very end here, how fast you can take data, right? The sample rate is important in a lot of applications. So purposely, a lot of the experiments that I designed for this lab are relatively low frequency, because as you know from maybe having studied in another course, how sample rates affect your ability to reconstruct signals, right? That's all based on the Nyquist criterion. So you want to be able to at least have collect data fast enough, right, so that you can actually get the right information in that signal. So again, Arduino has some limitations on that. So what we've done is, again, we've built this sort of system here where we are controlling the Arduino directly. There's a serial connector, right? Usually we use the USB. There's a program, right? A code that you will be using. Again, you don't have to know a whole lot about it, but PySerial is used for the Python side of being able to communicate serially with devices. And also the Arduino, of course, we know can send data serially out through the USB. That's what it's doing with the serial monitor, with the serial plotter, right? In fact, sometimes when we're taking data through this interface, you can't do serial monitor. I think one of the upgrades of Arduino 2, for example, is you could have two different serial communications going if you have the most up-to-date Arduino. So you possibly could be communicating serially with the computer and also showing serial monitor. But again, whether you want to do that or not it depends on the application. So we can now ask Arduino to be collecting data, right, in a little loop, always grabbing data from a sensors, and then we can be having it sent over to the PC. You can also have the PC in a Python program be sending commands to the Arduino to tell it, take data this way, sample at this rate, collect this number of channels. Remember that it's assumed whenever you pair the Python code with the Arduino that there's a particular code on Arduino that you are specifically addressing, right? So the code has to be the code on the Python has to be specific to the actual native code that's running on your Arduino. Okay. Nice thing is, once we get the data on Python, we can analyze it, look at it. You can be careful, again, mindful of the limitations of the Arduino platform in terms of how fast you can sample, the level of signals, and so on. But there's always higher grade, more costly hardware available that you might see in other applications, and just be aware of that. So building this Python Arduino serial communication, Arduino again can display data via the serial monitor. It's basically sending data to a serial port, and then again, as I mentioned, Arduino IDE 2 version 2 can monitor two connections together. So it used to be that if we were running this PySerial, we couldn't do that. I think you can do that now. And then also you have to be mindful of baud rates and what port you're using, right? And you need to tell the software on each side what the baud rate is and which port it's communicating through. Again, all of these things will be things that you'll quickly review in this first lab, and then we'll use them in subsequent labs. You get a better understanding of it. We always have three different programs running, right? We'll have a Python program that's controlling the acquisition of data and so on. There's another little Python program that you just import as a module that handles all the communications, and you never have to touch that. that receives commands from the first Python program and tells it, what kind of communications is going on, how to deal with the data, and so on. There's some functions in there. You never have to touch that one. And then there's the Arduino code, right? That's specific to a particular application. Again, and remember, that's the one that you have to use the Arduino IDE to upload to your Arduino, and then it just starts running. And then the Python program will say, hey, I hear you're running this program. Let me have some of that data. That's basically what's going on, okay? And then again, in Python, you can save that data. Remember, you can't generally save data on Arduino unless you have attached through it, maybe some kind of serial card or something. And then there's applications where you might do that with other Arduino platforms. You might save directly to an SD card or something. But what we want to grab that data right away and put it on by Python, view it, play with it, compare it to our simulations, and so on. I'm showing a couple of key lines that we do play around with, and that you'll have to make sure to change, right? And the port name here is going to be specific to your specific machine. So, for example, on a Mac, you might see something of this form. You have to find that once you have Arduino attached, right? You can get the port number. Make sure that your Python code has the right. It'll tell you, hey, I can't find a device there. It won't work. So make sure that you copy and paste in the correct port name. And then the baud rate, this has to match with what Arduino is set to, right? The data rate is there's the part of the code in Arduino that we're going to provide you can control, how fast each loop is occurring. So like if you have 50 on here, that's a 50 hertz rate of acquisition of data, and you can't go too high on that. I think the highest we've ever been able to go is about 400, and that's only if you're not doing that many things in each loop. And then you also tell it, how long you want to collect data. Okay, you say, hey, I want to collect data for about 10 seconds, and the program's going to start, and it's going to go and start logging data. It's going to timestamp it, and it's going to do all the things that Arduino the program has been designed to do. Okay, and then the data will come back in this sort of format here. So this is another line that we usually change for you, but usually this cap L, this F is the format. So it's a long word for the time values, and I think that's the F here means that this is a real number that the voltage is coming back in. This could also come back in an integer value sometimes. It depends on what. So all of these formats for data values, whether it's integer, long, words, etc. They're all defined in the Python program. Okay, the driver code will take care of all that for you. Finally, just a couple of things just to remember. I'm not in a previous course. You might have learned a little bit about A to D converters and so on. Usually, when you're working with A to D conversion, just be mindful of the resolution. That's the number of bits on the. That all has to do with. Let's say I'm measuring 5 volts. If I have an 8-bit converter, what does that mean? Be mindful of that. So, for example, if you had a DAQ device that had 16-bit, that means that you have 2 to the 16th levels that you can resolve voltage, right? If you have a 4-bit converter, then you have, it's a very crude resolution of a voltage value. So be mindful of resolution. This is what you pay money for. How fast you can sample is important, right? How many points you can collect, right? And as I showed you in that code, at least the sample rate and the number of points you want is important for the kind of data that you're trying to collect. And then there's other things on how you connect to the device, how you connect the signals onto Arduino. These are things we're practicing in the lab. How many channels can you actually sample, and then again, how do you deal with the data? So, these are all things that you have to think about in general about when you're setting up. And these are things, just keep in mind, this is what we're talking about when we're setting up this little experiment for you. As far as choosing a sample rate, you always hear, always sample at, the Nyquist says you have to have at least twice the highest frequency, and that's a minimum, right? So how does that work? Let's say you knew that a signal had, up to 60 hertz that was important. Let's say you had line noise, so you had 60 hertz noise and maybe up to 70. So that doesn't mean that I want to sample at just 120. Then that means that I can resolve that 60 hertz. It means that you can actually tell the difference between 60 hertz and any other frequency. So you might want to sample as high as possible. The minimum is 2, but you almost always want to go higher if you can. So, like I said, we're going to be sampling this fairly slow. We don't have to sample really, really high. And so sometimes you base it on frequency. And again, we just can't do a whole lot in terms of the concepts we introduce here. But just keep that in mind, that the way you think about it is what's the highest frequency that might be present in the data. We don't expect anything. This is a slow moving pendulum, about a 1 hertz natural frequency. And so we don't have to sample that high. So in terms of frequency, so 50 hertz is what we're going to be using, and that's way high enough. And since it's all, there might be some noise on there, but there's not a whole lot, so we're not going to care about resolving the noise. But so sample rates are important. I'm just going to skip over this slide in the interest of time. The other thing that sometimes is looked over is the resolution and time. So like, let's say this was the oscillation of the pendulum. We want to make sure that we have the delta t small enough. So let's say you were trying to find, hey, where does a peak occur? If you were resolving, let's say, data points, like this, then you might miss the absolute peak. So sometimes you want to be looking at both things: how fast, what's the frequency, but also what's that delta t. So like, let's say you knew that the period between these peaks was like, let's say 1 second. Then you can say, in order to really try to capture the absolute peak and not miss the peak, I want to make sure that my delta t is small enough. So that's something else to keep in time. So time resolution and frequency resolution, both important. Okay. Now I'm just going to show you, again, you can probably skip this part because you can always go back and look at this later, just to show you what the Arduino code looks like. And I know this is a lot to take in, but just so you can see, there's a loop here, okay? Here's the setup, and note that we're setting the baud rate, okay? What this program does is it has a loop, and there's 2 different options. One is it can start running, and if you send it a command and tell it, I want to look at the serial monitor, you can do that. But if you don't tell it to look at the serial monitor, by default, what it's going to do is it's going to start sending data, to the serial port. And so in this first option, so this says if, this is once the loop has been initialized, it's going to start doing this. It's going to try to give you a time. It's going to try to stamp the value, the current time here, using this function, micro s, gets the current time. And then all in here, here's the function that in analog val, it puts the value that you read from the pin, which we define up here, as the pin is pin 0, right up here. See, the pin is pin A0, so it's going to be collecting from the A0 port. So it reads analog voltage from there, and then this, you don't have to do this. You could keep, like, analog val is going to be an integer value of some type, right? And you could send that over and convert it later. But what we do is we go ahead and convert it into voltage here using this little integer to voltage conversion. And that variable is defined up here based on the fact that this is 0 to 5 volts. Then you say this is 1023 bits, right? So the voltage per integer values is 1024 levels. So you can, the conversion is between 5, remember it's 0 to 5 volts on analog input on Arduino. So that's how you can convert this to voltage. And then this right here sends data over serial line. So you would then send it, you're sending both values, the current time and the current voltage, only 2. And that's all that's being sent. And Python's going to be looking for those. And it's going to grab those, okay? This other version here, else if, is if you just want to send it to the serial monitor. And that's, something that you've done already in the previous lab, okay? So let me just jump one last thing here to this program here, which is one that is controlling your data acquisition. It's called Analog Pi Arduino DAQ driver. This is calling, see, it's importing Arduino DAQ from Serial Connect, and you don't have to change any of that. And that's a program that you can download from Canvas. And what this has is, see, here's where you put your port, here's where you put the frequency for your data rate and so on. And note, this is all you have to worry about is you have to give it the names of the data that you're collecting. You're collecting time and voltage, and the types right? And then this is what it's going to start doing. Down here, you never have to change any of this stuff down here, right? There's one thing here, the file name, that I put a general code in here where it just, every time you run this, it gives it a different stamp, like a timestamp. So it never rewrites any file that you might have collected. You could always change this and name it something else, right? The rest of this stuff, what it's going to do when you run this is it's going to start and it's going to count down. It's going to show you a countdown on the screen, and it's going to say, I'm going to start taking data. So you can, for example, you can hold your pendulum at 90 degrees and hold it there, and you can say run, and you run this thing. It'll start running, collecting data, keep it held, and then you let it go after it starts collecting data. That way it collects that little flat region of the voltage not changing, and then it'll start collecting. Make sure you know how long you need to collect data, because you're going to have to set this value here like 5 seconds or 10 seconds, depending on how long you want to collect data. Okay, and sometimes we run this program for different applications for up to 180 seconds or much longer, and it'll just keep monitoring that Arduino, grabbing that data, and then it'll drop it into that CSV file. Okay, that's basically how this all works, and then you get to play with this in the lab.